In this video, we're going to learn how to do proofs by contradiction. Proof by contradiction is a very powerful method, but we have to be careful when we use it. That's why first I'm going to explain to you the main ideas involved in doing a proof by contradiction. Then I'm going to give you two examples. And finally, I want to compare proof by contrapositive and proof by contradiction, the pros and their cons. Okay, so what is the idea behind a proof by contradiction? Well, instead of showing that the statement is true, we're going to show that the statement is not false. We know that statements are either true or false. So if the statement cannot be false, then it has to be true. It's kind of sneaky way of proving that something is true. So how can we proceed to do that? Well, we're first going to assume that the statement is false, or which is the same thing as assuming that the negation of the statement is true. Then we're going to proceed as we would with a direct proof. We're going to get that one statement follows logically from the next, maybe some algebraic manipulations. You do what you need to do until eventually you're going to arrive at a contradiction. And if you know that you did all the steps correctly, that you didn't make any mistakes in your proof, then you know that the reason why you arrived to a contradiction is because your assumption was wrong, meaning that it is impossible for your statement to be false. And then at the end, well, we need to conclude. We need to state that because of the contradiction, it can't be the case that the statement is false, so it must be true. So let's get started with our first example. Here we're going to show that there is no smallest positive real number. And in the proof, the first thing that we say is assume for the sake of contradiction that there exists smallest positive real number. And here, assume for the sake of contradiction, when we said it, we're letting the reader know that this is the proof methods that I am using. I'm using a proof by contradiction. Okay, so now we're assuming that there exists the smallest positive real number. Let's try to unwrap it and see what this means. Well, this means that there exists a positive real number such that this positive real number r is less than or equal to x for any positive real number x. Okay, so now that we have this, our goal would be actually to construct a positive real number that is smaller than this smallest positive real number. So to do that, we're going to define s to be r over 2. Okay, since r is positive, then r over 2 is also positive, and also r over 2 is less than r. Therefore, we have found a positive real number s such that s is less than r. But that contradicts the assumption that r is the smallest positive real number. Therefore, there is no smallest positive real number. And in this example, we can see one of the beauties of proof by contradiction. Proof by contradiction is very, very useful when we want to prove that something doesn't exist or that something is impossible. Because you see, when you want to prove that something doesn't exist, when you assume the negation, what you're assuming is that that thing exists. And now you have something concrete to work with. And those cases, yes, try proof by contradiction is very likely to be successful. Because as I said, when you want to prove that something doesn't exist, when you assume the negation, you assume that that thing exists and you can manipulate it. Now let's take a look at another example of how we can use proof by contradiction to prove a conditional statement. So we have this theorem that says that if a and b are integer numbers, then a squared minus 4b is not equal to 2. So here again, we have a statement that is in a negative way, right? It's telling me that it's not equal to. But working with things that are not equal to is very often much harder than things that are equal to something. So whenever you see a statement that is written in a negative way, you will think, oh, I should use proof by contrapositive or proof by contradiction. So how can we do this by contradiction? Well, we're going to assume for the sake of a contradiction that a and b are integers and a squared minus 4b is equal to 2. Why did I assume this? Remember, we are assuming the negation of our statement, and the negation of a statement of the form if P then Q is P and not Q. If you're having trouble remembering what the negation of a conditional statement is, please make sure that you take a look at the video where I explain the negation of conditional statements. Okay, so now we have two things to work with. We know that a and b are integer numbers, and we know that a squared minus 4b is equal to 2. Okay, let's see what we can do here. Well, if I know that a squared minus 4b is equal to 2, this implies that a squared is equal to 2 plus 4b. But I can take two common factors, so I end up with 2 times 1 plus 2b. That tells me that a squared is even. But remember that we showed that if n squared is even, then n is even. So in this case, then I conclude that a is even by previous results that we already proved. Perfect. So now that we have this, we know then that there exists an integer k such that a is equal to 2k. And I'm going to substitute this back into my original equation, and then we have that a squared is 2k, right? So we have that 2k squared minus 4b is equal to 2. But well, this implies that 4k squared minus 4b is equal to 2. Taking a 2 common factor, we have that 2 times 2k squared minus 2b is equal to 2. And if I divide by 2 on both sides, I end up with 2k squared minus 2b is equal to 1. Can you see where I'm heading here? Can you see what the problem is? Well, if I take 2 common factor, I end up with 2 times k squared minus b is equal to 1. But k is an integer, so k squared is an integer. B is an integer, so k squared minus b is an integer. So we're saying that 1 is equal to 2 times an integer. That means that 1 is an even number. But this is a contradiction. We know that 1 is not even. 1 is odd. Therefore, this contradiction tells me that it is true that if a and b are integer numbers, then a squared minus 4b is not equal to 2. And here you see, we use a result of something that we already learned when we were doing proof by contrapositive. So this here in this example, we're building up from things that we did in the past. And this is something that is going to happen very often in this module. So that's why it's very important to stay on top of the material, because every time we're going to be using things from previous videos. Okay, now that we have these two examples, let's try to see what is the difference between a proof by contrapositive and a proof by contradiction. First one, proof by contrapositive only works for statements of the form if P then Q. But proof by contradiction works for any kind of statement. Like if we want to prove that, as we did before, that there is no smallest positive real number, proof by contradiction is very well suited for that. Now, let's compare the two when we're trying to prove a statement of the form if P then Q. Okay, so proof by contrapositive, we have one assumption to work with, which is not Q. Now, in proof by contradiction, we have two things to work with. We have P and not Q. So sometimes that could be helpful. Now, in a proof by contrapositive, we have a clear goal. We know that we start with not Q, and we know that we want to arrive to not P. Whilst in a proof by contradiction, we are not sure of where we have to get to. We have to get to a contradiction, but we don't know beforehand what the contradiction is going to be. And sometimes we might even miss the contradiction and try to continue working without realizing that we arrived at a contradiction a while ago. Another problem is that if you make a mistake in your proof, you could arrive at a contradiction, not because the statement was true and your assumption was incorrect, but because your mistake led you to a contradiction. So whenever you're doing proof by contradiction, make sure that you're very, very careful and that all your steps are correct. Because as I said, a mistake in the middle of the proof could lead you to a false contradiction. Okay, and now I want to tell you a few things that you need to keep in mind when you're using indirect proof. First of all, a direct proof is usually preferred over an indirect proof, unless this indirect proof makes the proof a lot clearer or shorter. Always let the reader know what proof technique you are using. If you are using a proof by contrapositive, tell the reader we're going to prove the contrapositive, which is unstated contrapositive. If you are doing a proof by contradiction, let's say, assume for the sake of a contradiction that and then you say what you're assuming. Please, please, please be careful when negating statements. These two proof techniques rely heavily on you negating statements correctly, so you have to be extra careful. One important note, I see many students making this mistake, and I don't want you to make it, is that when they're proving the statement of the form if P then Q, if you assume not Q and this leads you to not P, this is not a proof by contradiction. It is a proof by contrapositive. So please make sure that you don't call a thing a proof by contradiction when in reality it is not. So whenever you assume not Q and you conclude not P, this is a proof by contrapositive, no by contradiction. And well, that's it for the indirect proofs, and make sure that you practice and do lots of proofs so you become more confident in working with these type of problems.